Recent observations of the interstellar comet known as 3I/Atlas have drawn renewed attention from astronomers after the object appeared to develop a faint bluish hue, a subtle but intriguing change that may point to new physical processes occurring on or around the comet. This apparent color shift comes shortly after the comet experienced a rapid and unexpected brightening event while it was hidden behind the sun, beyond the view of most Earth-based telescopes. What makes this development particularly interesting is that this is now the third time scientists have reported a potential change in the comet's coloration since its discovery, yet none of the previous color variations were conclusively confirmed or proved to be long-lasting. As a result, researchers are approaching the new findings with cautious excitement, aware that interstellar objects often defy expectations and challenge existing models of cometary behavior. 3I/Atlas holds a special place in modern astronomy, as only the third confirmed interstellar object ever observed passing through our solar system, following the discoveries of Oumuamua in 2017 and 2I/Borisov in 2019. Unlike typical comets that originate from the Kuiper belt or Oort cloud, 3I/Atlas is believed to have formed around a distant star, somewhere in the outer regions of the Milky Way. Scientists estimate that it may be more than 7 billion years old, potentially making it older than our own solar system. At some point early in its history, gravitational interactions within its home star system likely flung it into interstellar space, where it drifted for billions of years before its chance encounter with our Sun. This immense journey means that 3I/Atlas carries with it pristine material from another planetary system, offering a rare opportunity to study matter formed under conditions very different from those that shaped the planets and comets closer to home. The comet was first detected in early July as it hurtled toward the inner solar system at extraordinary speed, traveling at more than 130,000 miles per hour, or about 210,000 kilometers per hour. This velocity alone confirmed its interstellar origin, as objects bound to the Sun cannot reach such speeds relative to our star. Early observations suggested that 3I/Atlas behaved broadly like a comet, with a surrounding cloud of gas and dust known as a coma, forming as solar radiation heated its surface. However, from the beginning, astronomers noticed subtle differences in its brightness, structure, and spectral signatures when compared with comets native to our solar system, hinting that its composition might be unusual. In early October, 3I/Atlas made a relatively close approach to Mars, providing an additional observational opportunity for spacecraft orbiting the red planet. Shortly after this encounter, the comet moved to the far side of the Sun from Earth's perspective. For several weeks, it was largely unobservable by ground-based telescopes, as the Sun's glare overwhelmed any faint light reflected or emitted by the comet. During this period of solar conjunction, astronomers expected the comet to continue its gradual brightening as it moved closer to the Sun, driven by increasing solar heating. What they did not expect was the dramatic brightening event that appears to have occurred while the comet was hidden from view. According to a recent analysis conducted by a pair of researchers using data from space-based observatories that could still monitor the comet, 3I/Atlas brightened by several orders of magnitude during its time behind the Sun. This level of brightening cannot be fully explained by its decreasing distance from the Sun alone. The comet reached perihelion, its closest point to the Sun, on October 29th, at a distance of about 130 million miles, or 210 million kilometers, roughly 1/4 times the distance between Earth and the Sun. While this proximity would certainly increase sublimation of surface ices, the magnitude of the observed brightening suggests that an additional process may have been at work, such as a sudden outburst of gas or fragmentation of surface material exposing fresh, volatile-rich layers beneath. It was in this same study that researchers reported the surprising observation that 3I/Atlas appeared to be distinctly bluer than the Sun, a characteristic not clearly seen in earlier observations. In astronomical terms, a bluish hue often indicates the presence of specific gases that emit or scatter light more efficiently at shorter wavelengths. For comets, blue coloration is commonly associated with molecules such as carbon monoxide, ionized carbon, or ammonia, which can glow blue when excited by solar radiation. The researchers suggested that as the comet heated up, it may have begun releasing a different mix of gases than before, temporarily altering its observed color. This is not the first time that a potential color change has been reported for 3I/Atlas. Since its discovery, astronomers have noted at least 2 earlier instances where the comet appeared to shift in color, only for later observations to show that the effect was either transient or within the margin of observational uncertainty. Such fluctuations can be caused by changes in viewing geometry, dust production rates, or instrumental limitations, making it difficult to determine whether a true physical change has occurred. As a result, the newly reported bluish hue remains unconfirmed by independent teams, and the study describing it has not yet undergone peer review. Nevertheless, if the color change is real, it could provide valuable clues about the comet's composition and internal structure. Interstellar comets are expected to contain ices and minerals that formed under different temperature and chemical conditions than those found in our solar system. The release of carbon monoxide or ammonia, for example, might indicate that these volatile compounds are more abundant or more deeply buried within 3I/Atlas than in typical solar system comets. Alternatively, the extreme thermal stress experienced during its close passage to the Sun could have triggered chemical reactions or structural changes that temporarily altered the comet's appearance. The apparent brightening and possible color shift also raise questions about the physical integrity of the comet. Sudden increases in brightness are sometimes associated with fragmentation events, where parts of the nucleus break off, increasing the total surface area available for outgassing. If 3I/Atlas experienced such an event while hidden behind the Sun, it could explain both the unexpected brightening and the release of new gases that changed its color. However, without direct imaging or additional spectral data, this scenario remains speculative. As 3I/Atlas gradually emerges from behind the Sun and becomes more accessible to Earth-based telescopes, astronomers are eager to gather more data to confirm or refute the latest findings. Continued monitoring will help determine whether the bluish hue persists or fades, as happened with previous reported color changes. Spectroscopic observations, in particular, will be crucial in identifying the specific gases present in the comet's coma and assessing how its composition evolves as it moves away from the Sun regardless of the outcome. The study of 3I/Atlas highlights the scientific value of interstellar visitors. Each such object provides a rare, fleeting glimpse into the building blocks of distant planetary systems, carried across the galaxy by chance encounters and gravitational forces. Even ambiguous or short-lived phenomena, such as tentative color changes, can offer important insights into how these ancient travelers respond to the environment of a new star. As observational techniques improve and detection rates increase, astronomers hope that future interstellar comets will be discovered earlier and studied in greater detail, allowing mysteries like those surrounding 3I/Atlas to be unraveled with greater confidence.